Propositional logic. What is it? What is a proposition? A proposition is a declarative sentence that is either true or false. So it is a sentence that we can decide whether it is true or false. Okay, so it has to take one of these values. And we will call these values the true or false. We will call them the truth values. The truth values, which means either true or false. These are called the truth value. Not necessarily it is a true, but we are calling it a truth values, which is true or false. Let's see. First example. Muscat is the capital of Oman. Is that true? Yes. So it has taken a truth value. So it is a proposition. So we are making examples for propositions. The sky is green. False. So it is a sentence, a declarative sentence that has taken a false as a truth value. So it is a proposition. It doesn't matter whether the sentence is false or it is true. It takes one of these, so that we call it as a proposition. 1 plus 1 equals 2. That's it, true. Okay, so it is a proposition. 2 plus 3 equals 4, which is false. So it is a proposition. It has taken a truth value. Okay, these are examples of not sentences that not propositions. What is today? So that is a question. We cannot say it is true or wrong. It is a question. Clean your room. No, there is nothing true or false about that. So this sentence is not a proposition. X plus 1 equals 2. This one can be true and can be false. If x equals 1, then it takes the value true. If x equals 3, for example, then the sentence is false. So it can either be true or false. So we cannot decide. So it is not a proposition. Okay. X plus y equals z. Well, that equation might be correct or not, depending on the values of x, y, and z. So it does not take a truth value and stay on that. It might take true or false. So we cannot decide. We cannot decide because x and y and z are not given values here. Okay? So this is also not a proposition. So every one of these is not a proposition. Okay. Now propositions will be the very basic statements that we will work with. So we will give them letters. So I mean by we will give a sentence which is a proposition, we will denote it by letters like Q, P, or Q, or R, S, T, small letters. Okay? So for example, we will say P, we mean by letter P, for instance, this letter P, we mean the following sentence. Ali is taller than Ahmed. We don't know whether this statement is true or false, but it has to be either true or false. If Ali is taller, then it is true. If Ahmad is taller than Ali, then it is false. So it is a proposition. Now we gave it this letter. Okay. R. This denotes another sentence. 3 divides all integers. This is a proposition, which is false. Okay. Or Q. We will denote the letter Q, the following proposition. Faris is younger than Ali. Well, we don't know. It might be true or false. But it has to take one of them, so we call it a proposition. We can decide at the end. S represent the following sentence. 2 times n plus 1 is odd for any integer. And this is true. So, and okay. And this is false. And for these ones, we need to know who's Ali and who's Ahmad to decide. So what I wanted to say here that sentences, or more precisely, propositions, are denoted by letters. We agree with that? Okay, so small letters means a sentence, which is a proposition. Okay. Now, what we are going to do with the propositions, we will do some composition of propositions to obtain compound propositions. What I mean in here. Okay, what do I mean? So assume we have P and Q represent propositions. Now what we do, we will define what the negation means, conjunction, disconjunction, and exclusive OR. Each one of these are called logical operators. Why we call them logical operators? Because it take propositions and combine them together, two propositions or even one proposition, and make a combination out of them. Okay, once we do that combination, we obtain compound propositions. So compound propositions are formed from existing propositions using logical operators. So what are these logical operators? Very easy. They are very easy to define. First one is the negation of P. So given a proposition P, what is the negation of P? Is written this way. Let me rewrite it here. This is not P, and it is read not P. So this is not P, and this notation here means we are negating the proposition P. So it means it is not the case that P. So proposition not P. So here we go. It is written not P, and the truth values are as following. If P is true, then the negation is false, and if P is false, then the negation is true. So this is the negation. Okay. Another conjunction, another logical operator, again logical operator, which is the conjunction of P and Q. We have P a proposition, Q a proposition, and we want to make the conjunction P and Q. Let me rewrite it here. P and Q. That's the way we read it. P and Q. Okay? So this statement here simply says this conjunction is true when both P and Q are true and false otherwise. Okay? So we are making a conjunction here, but the conjunction of two propositions will never be true unless each one of the two propositions is true. And this is demonstrated in the following table. Here, this represents the truth value of P. It might be all the possible cases, and Q. So we might have true and true, true and false, false and true, false and false. These are all the possible combinations of the truth values of two propositions. So true and true will give us true. True and false will give us false. False and true will give us false. False and false will give us false. Let's see examples to make this clear. Let's make the sentence P to be 5 is an integer. And let's make the other statements to be 5 is an even integer. Okay, so let's see. 5 is an integer. This is a true value. Yes, it is an integer. عدد صحيح. 5 is an even integer. It is false. Okay, now P and Q represent the following statement. 5 is an integer and it is an even integer. So is that whole statement true? The whole statement is false. 5 is an integer, this is true, and it is an even integer, this is false. So the whole statement becomes false. That's why true and false gives false, and false and true also gives false. And clearly false and false will give a false statement. Okay. So you need to have this in mind all the way. The conjunction, the and, is true only when both proposition is true. Now here another logical operator, which is the disjunction of P and Q. And here it is. This is P or Q. P or Q. It is read this way, P or Q. And this says this conjunction is false whenever both are false, both propositions, and true otherwise. So it is false when both of them is false. But if any of them is true, then the disjunction is true. And what that means, now look in here, both of them are false. Both of them are false, so I will say false and or false will give us false. Now the remaining will be true. True or true will indeed give me a true statement. True or false will give me a true statement. False or true will give me a true statement. So if we use this example above there and we write P or Q, that statement will be 5 is an integer, or, so I have this for this or in here, while I have and for this conjunction in here, or 5 is an even integer. So is that statement true? So 5 is an integer or it is an even integer. The whole statement is true because it says 5 is an integer or, so one of them is true. So the compound statement is true. Okay, good. Now, before I keep moving, I would like to use, again, I want to use this statement here to find the truth values of the following: P and not Q, not P and not Q, not P or Q, not P or not Q. So what are the truth values of all of these? So P is true, so that means true, and Q is false, so not Q is true, and that will be true. Okay, so notice not Q is true. Okay, now for this one here, not P is false, not Q is true, so we'll have false and true, so we'll have false. Okay, again, not P is false, while Q is false. So we have false or false that give us false. Here, not P is false, not Q is true. So we'll have false or true, and that give us true. Good? Okay. One more logical operator, which is the exclusive OR. In fact, we will not be using this for the remaining of the course, but we will see it here. Okay? Exclusive OR, but it is interesting, of P and Q. And it is written this way, P, so we use this notation, and it is read P XOR Q. And this proposition is true when exactly one of these is true. Here we go. T XOR T gives false. True XOR true gives false. Do you believe it? Okay. We will see why. Maybe I shall not. I shall use this notation. Maybe I shall not use the I will use that. Okay. T true XOR false give us true. False XOR true give us true. False XOR false give us false. The statement here says it will give us true only when exactly one of them is true. If both of them is true, then the XOR is false. If both of them is false, then the XOR is false. Why is that? This example will illustrate why this is true. Now, the statement P says, I will use all my saving to travel to Europe. Okay, so you have some saving. Then you will use it to travel to Europe. This proposition P says. While proposition Q says, I will use my saving to buy an electric car. Therefore, you have to do something. You decided to do something with your savings. But you cannot do both. You cannot go to Europe and buy an electric car. You cannot do that because your savings are enough to do one thing. So, if we assume true that you will go to Europe and true that you will buy an electric car, then the whole statement is false because you cannot do both things. That's explain why this false is happening here. Okay. So, and we said also you decided, we are assuming that you must do one of them. You must use your savings. So you cannot say, okay, I don't want to go to Europe and then I also don't want to buy an electric car. So that's false and false. And the whole statement is false because we are assuming one of these two things must be happening. Either going to Europe or buying an electric car. And that's why we get it true exactly when one of them is true. If you go to Europe, then you cannot buy electric car. So going to Europe, that proposition is true, while buying electric car is false. If you buy the car, then you will not go to Europe. Now, the proposition of buying the car is true, and the proposition of going to Europe is false. So, the whole compound statement will be true only when you do one of these things and don't do the other thing. This is why it says is true when exactly one of the P and Q is true. The conditional statement. One more logical operator. What is the conditional statement? Here we go. The conditional statement, P gives Q. We can read it this way or in some other ways. Here we go. If P, then Q. Let me write this here. If P, if we have P in hand, if we have P happening, the proposition P happening, then Q will be happening also. Okay? This is called the conditional statement because it has an if. And this conditional statement is false only under one case. Whenever P is true and Q is false. Here we go. This is the only case where the conditional statement is false. If true, then false. If true, then false will give us false. Okay? We'll see this again. Now we have here P gives Q. Again, this is the conditional statement. We will call the given proposition, which is the given information, we call it hypothesis. So we need to know this word. And what's happening after having P, then we conclude something, which is Q. So we call Q conclusion. Okay. And again, it is read if P, then Q, or P implies Q. We read it this way, or we read it this way, or Q happening whenever P. But we will most of the time say if P, then Q, or P implies Q. Okay? Let us see an examples. Let us see some examples to make us understand this clearly. Example. Let us use P that sky is raining. Okay? Q, sky is cloudy. Okay? Then we can say P gives Q. That means if the sky, let me write it this way. If the sky is raining, then it is cloudy. And that statement is true, right? Okay. So true gives true. If it is true, then that means the sky is raining, so it is cloudy. Okay. I want to demonstrate other examples for this because we will come back to them. So let me say this is example 1. Example 2. P, I live in Muscat. This is the proposition P. Proposition Q, I live in Oman. So P gives Q means if I live in Muscat, then I live in Oman. Okay. Now, if we go to let's go back to the table of the truth values of the conditional statement. We did not go over it completely. So, True gives true, that is a true statement. False gives true is a true statement. False gives false is a true statement. Isn't that strange? So how come, for instance, false gives true is a true statement? Which means in here, if we want to apply it, in here we will say false. Let's assume the sky is raining is a false statement. The sky is cloudy is a true statement. So can we say if it's raining, this is false, it's not raining, then it is cloudy. It is, sorry, if I'm sorry, I should not say it that way. Let me not assume that. What? Okay. Let me go back, and I wanted to say, let's assume. Okay, what's happening now? Okay. Let's assume this is true. Okay. Okay. And this is true. So it is raining, and so the sky is cloudy. What if we assume it is not raining? Not raining. And then we conclude for a while it is cloudy. Okay? And we are saying this is false gives true because we assumed it is cloudy, and then the result is true. So how come this statement here, it's not raining, then it is cloudy? We take it as a true statement because it could be cloudy but not raining. That's natural. Okay, this is the kind of explanation why this is happening. If we want to understand why this is happening, if we say it is not raining, then it is not cloudy. That's a good statement. That's a true statement. No problem with it. Okay. Now for the conditional statements, we have the following variations. The contrapositive. Okay. Now given the conditional statement P gives Q, the contrapositive of P gives Q is not P gives not Q. So what we do, P gives Q. P gives Q. So the contrapositive is the following. We replace the P and the Q, we replace each other, and we negate each one of them. So we replace the places, we change the places of P and Q, and we negate both of them. Then we get to the contrapositive. This is called the contrapositive. So again, I would like to write it. P gives Q, write it here. The contrapositive is not P gives not, sorry, not Q, sorry, gives not P. So not Q gives not P. This is called the contrapositive. Okay? And let's see about the truth values of the contrapositive. In here we have true and true gives it true. So in here we have already the conditional statement. So true and true gives true, true and gives false is false, false gives true is true, and false gives false is false. What we want to do now, we want to find the truth table of the contrapositive of this one here. Not P gives not Q. To do so, we need to find what is not Q. So this is Q in here. So not Q is we obtain by negation. So negating true will give us false. Negating this false will give us true. Negation here of this give us false. and the negation here will give us true. Now we negate P, and P is in here. This is P. Negate P, we get false, false, true, true. Okay, because this is negate this, we get that. Negate this, we get that, and so on. Now, what we're gonna do is to see what not P implies not Q, whether this statement is true or false. Let's start. This is not Q and this is not P. So false implies false. We have seen it. It is true. True implies false. We have seen it. It is false. False implies true. We have seen it. It is true. And true implies true is true. Now notice the following. This compounded statement not P gives not Q, and this compounded statement P gives Q, they have the same truth values. They have the same truth values, corresponding or fixing to the same truth values of P and Q. So therefore, these two statements, P implies Q and not Q implies P, are equivalent because they agree on the truth values. And I would like to write it the following way. P implies Q, and we will learn that, is equivalent, these are three lines, to not P gives not Q gives not P. This is very important and we will use it a lot. It is called contrapositive. So the conditional statement is equivalent to its contrapositive. Okay? And we will go back to the examples we have just seen and apply that. But before we do so, let's see more definitions because we want to apply them all together. Okay. Now, assume again we have a conditional statement P gives Q. We want to define the converse. The converse of P gives Q is Q gives P. So P gives Q, or Q, the converse, is Q gives P. Question: are they equivalent or not? To find out, we will find the truth table. So we already have the truth table of P gives Q according to the truth values of P and Q. Now here I want to compute Q gives P, and I have them in order in here. So true gives true is true. False gives true is true. True gives false is false. False gives false is true. Now notice here that they do agree in here and in here, but they do not agree for these two parts. And therefore, P gives Q and Q gives B are not equivalent because they don't have the same, they are not equivalent because they don't have the same truth values. Now this is called the converse. The converse is just replacing the statements, the propositions. P gives Q, the converse is to say Q gives P. But the contrapositive was replace the places and negate. Okay. Now one more, which is the inverse of the conditional statement. So if we have a conditional statement, P gives U, then the inverse is the proposition not P gives not Q. So in here we did not change places. We kept the propositions as they are, but we negated each one of them. So the statement was P gives Q. The inverse is not P gives not Q. And the question, are they equivalent? And to answer that, here we have P gives Q according to the truth values of P and Q. And we want to find the truth values of not P gives not Q. So we need to compute not P. P here is true, so negation is false. P is true, negation is false. So this is true, the negation in here, negation is true. Okay? Again, we want to negate Q. Q is true here, so negation is false. It's false here, negation is true. So true, false, and then false, true. Now to compute this here, this compounded statement, that means we go the following way. False gives false, this is true. False gives true, false implies true is true. True implies false is false. True implies true is true. Now notice that these two statements do not agree at these two parts. So P implies Q, not P implies not Q. They are not equivalent because they do not agree on the truth values. Now let's go to our example above there, to one of them, and do all these things that we learned for this example. So what is the contrapositive here? So we want to have the contrapositive. The contrapositive says not Q gives not P. So I want it as a sentence. Q says I live in Oman. So not Q says I do not live in Oman. So if I do not live in Oman, then, so again, this is the negation of Q. Then, now I want the negation of P. What is it? P, I live in Muscat. The negation, I don't live in Muscat. Then I do not live in Muscat. Okay? Now, what about the inverse? What next we learn? The converse. The converse was changing the places only. So the converse will be Q gives P. Now what is Q? Q, I live in Oman. So the statement will become, if I live in Oman, this is Q, then I live in Muscat, and this is P. So this is P and this is Q. And you know this statement is not necessarily true. You might be living in Oman but not necessarily living in Muscat. You might be living in some other city. So if I go back to this statement also, I will say this is not Q and this is not P. Okay, now what's left? The inverse. The inverse of this statement The inverse, we said we keep the places of the propositions, but we negate each one of them. So the inverse is not P implies not Q. So the statement becomes not P means I don't live in Muscat if I do not live in Muscat, then not Q is the negation of Q, then I do not live in Oman, and we know this is a wrong statement. So this is not P and this is not Q. Okay, so it is important that you remember how to formulate, if you are given a conditional statement, how to formulate the contrapositive, the converse, and the inverse. And it is important you don't confuse them with each other. The biconditional statement. Biconditional means two conditional statements in opposite directions. So if we assume P gives Q and then we say also Q gives B. Here we go. So the biconditional statement, P if and only if Q. This is the way we read it. P if and only if Q. So P gives Q and also Q gives P. So it has two conditional statement being conjuncted to each other. B gives Q and Q gives P, which is the converse. So the conditional statement and its converse are happening together. Okay? And this is the truth table. And in here it briefly says this statement is true when P and Q have the same true values, when each of them is true or each of them is false. These are the only cases where the biconditional statement is true. Otherwise, it is false. Here we go. It is defined this way. True if and only if true, the whole statement is true. False if and only if false, the whole statement is false. But true if and only if false, this is false. False if and only if true, this is also false. Okay? Okay. Before we give an example for that, let us make sure that if we really combine these two statements together with a conjunction, then with this conjunction we get the values, the truth values we claimed. And we do it here. Now in here P gives Q is computed, we already know it. Let's compute Q gives P. So this is Q and this is P. So true gives true is true. False gives true is true. True gives false is false. False gives false is true. Now what we do to obtain all that, we will do the conjunction of this and this. So we'll have true and true gives true. True and false is false. False and true is false. True and true is true. And if you notice, true, false, I need to fix that. This is true and true is true. Now if you notice, this is true, false, false, true, and it is the same in here. While we have the truth values of P and Q and are listed in the same order. And an example of the biconditional statement, let's make the following example. Let the statement P be 2 divides an integer n, Q n is an even integer. So clearly these two statements are equivalent. If P is true, then Q is true. So this is the way we say it. 2 divides n, that gives n is an even integer, and also if n is an even integer, then 2 divides n. So we go the other direction. Now notice here, if you negate both of them, negate this. Okay, so let me write in here, that means P if and only if Q. Now what about if we negate both of them? Not P if and only if not Q. And we say we'll have false if and only if false, and that is true as we claim here. So what the sentence will become? Negating B, that means 2 does not divide n. Negating Q means n is an odd integer, and these two statements are equivalent. So the truth table of compound proposition, we have done one already actually, how to compute whether a compound proposition is true or false depending on the truth values of the propositions involved in that compound proposition. So we mean the propositions are P and Q. We are combining them together using the AND, or negation implies. You see in here in this example we're using the disjunction, which is the or. We are using the negation, not P. We're using the conjunction, P and Q, and then we're using implication. So we are using the 4 logical operators to make a compound statement out of P and Q, and we want to see the truth values of this compound statement. So to do so, first we list the truth values of P and Q this way: true, true, false, false, true, false, true, false. You may ask me, what if we have 3 propositions? How we list the truth values for them? And I will answer that in a while. Okay. Now to evaluate the truth values of these, we look at the components. So first thing, we need to know the truth values of not Q. So Q in here, so not Q is as following. Just we negate the truth values of Q. Now next we need to know the truth value of this part in green in here, which is here. Now we will make this conjunction between P and not Q. So we will have an I on P in here and not Q in here. And then we have or. True or false is true. This is what I want to write here. If we have any statement P or true. So whatever the truth values of P, the result will be true, because whenever we have that or the disjunction will be true if one of the sides is true. And if two of the sides are false, this is the only case where it is false. Okay. Now, true or true is true. False or false, this is the only case it is false. False or true is true. Okay. Now we go to evaluate P and Q. So we'll have I on P and I on Q. P and Q. So it is true and true. True and true is true. Here, true and false is false. So this is what I wanted to say here. P and false, whatever the truth value of P is, this is always false. Because with the and, with the conjunction, if one of the sides is false, then the result is false. False and true is false. False and false is false. Okay. Now, to accomplish this, we need to say this gives that. So true gives true is true. True gives false is false. False gives false is true. True gives false is false. And then we have the truth table of this compound statement. So this is the way. Now, precedence of logical operator, which means which goes before which. When we have logical operators being together, which one we perform first. This table in here, it tells you which one goes first. So the priority, first priority is given for the negation, second priority for the conjunction and, third priority for the disjunction, fourth priority for the implies, and then for the biconditional. So for instance, for this one, we must go for the negation first. So it means this, but not that. So we will do the negation and then we will do the and, because the negation will precede the and. We cannot do this. We are not allowed to perform the and then the negation. No, the negation must come before the and. Okay. Now in here we must perform the and before the or. Right? Here we go. The and then the or. We will not say, okay, because this comes to the left, so we will go for it first. No, this is wrong. We cannot do this, because we say the conjunction precedes the disjunction. Okay. Again, in here, the conjunction precedes the disjunction. So we will go for and, P and Q, and then we take or R. We will not allow to go for the disjunction first. Okay. Again, we will go for the disjunction before we go to the imply, right? Because the disjunction precedes the imply. So we go for disjunction and then we go for the conditional statement. We cannot say, oh, okay, because this comes to the left, so we go for these two first. No, this is wrong. And again, same thing here. We go for the disjunction and then we go for the imply. This is good. And we cannot go the conditional statement before disjunction. Okay. Now in here, what do we have in here? This is the same thing. This is repeated. Yes, this is repeated. Actually, it is the same as in here. Okay. And the last part of this section is logic and bit operation. So if we represent it true by 1 and false by 0, then the OR will be that means false and false. The or will be false, 0, or 0 will be 0, and this will be 1, this will be 1, and this will be 1. That looks like addition, but the result is 0 or 1. But this looks like multiplication. So this is 0, 0, 0, and 1. The XOR will be 1 in here and false and 0 in here. The XOR look like addition modulo 2. What is modulo 2? We will learn later what is modulo 2. And now if we go and make the OR in here, anybody have a question? Okay. So for the OR in here, that means 1, 1, 1, 0, 1, 1, 1, 1, 1, 1, right? This is for the OR. And for the AND, this is 0, 1, 0, 0, 0, 1, 0, 1, 0, 0. And for the XOR, try to do it by your own. And if there is any mistake, please correct me. And this is what we want to discuss for today's lecture. Now, what if I ask you to make the following truth table? Find the truth table of the compound proposition, which is P or Q let me just make it and S this way, P or Q and S. And I could test you on some other thing. I could write it just this way, P. Oh, okay. If I write it, okay, that's that. Okay. If you see it this way, then which way you think about? This is the same as. So which one goes first? This is P or Q and S, right? Because the AND goes before the OR. Okay. Now we have three propositions here: P, Q, and S. How you make the truth table using three propositions? So to make the truth table of this statement here, we need to use the following proposition: P, Q, and S, right? And then we will say, okay, we want Q and S, and we have P, so we have P or Q and S. Now the idea here, how do I list the truth values of each of P, Q, and S? So what we do, actually, we must have 8 cases. How do we know we must have 8 cases? Because we have 3 propositions, 1, 2, 3. So we have 2 to power 3, and then we have 8 cases. We have 8 cases to consider. If we have 4 propositions, then we have 2 to power 4. Okay? And why is that? Because each proposition will take 2 possibilities. Okay? So if I want to explain that here, So first proposition, so let's assume we have four propositions. Say they are P, Q, S, and R. Okay, so each one of these propositions, each one of these four propositions will take two values, either true or false. So we have two possibilities here, and we have two possibilities in here, and two possibilities in here. So the number of all possibilities is 2 times 2 times 2 times 2, and then that's 2 to the power 8, and then we have 16 cases. So we have 16 cases whenever we have 4 propositions. When we have 3 propositions, say P, Q, and S, then we have 2 cases for each one of them. So we'll have 2 times 2 times 2, so that means 2 times 3, so we have 8 cases. Okay, why do we need that 4? So 8 cases. So what we do, we will go to the very last proposition and say, okay, this will take true, false, true, false, and then we keep interchanging that alternatively. True, false, true, false, true, false, true, false, then we are done. Then these are 8 cases. Okay, so for the very first variable at the right, we changed true and false alternatively, one after another. For the second from the right, we will change but every 2. So we have true, true, false, false, true, true, false, false. Okay, false, false. And for the last one, we will change every 4 times. So we have 2, 2, true, true, false, 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 false. Okay, so the very first one to the right, change true and false alternatively every each time. When you move to the variable to the left, you change every 2 times to true, false, false, true, true, false, false. When you move to the left one more, you change every 4 times. And now if you have 4 variables, as in here, R will change every time, every other time. True, false, true, false, true, false. S will change every 2 times. True, true, false, false, true, true, false, false, and so on. Q will change every 4 times. True, 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 false, 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 and again true, 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 false, 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 because we have 16 cases. And now P will change every 8 times. Okay, I will let you think about that. And then now you can complete this truth table, and let's see Q and S. This is true, this is false. Q and S, I will leave the remaining 2. Now in here I have P or Q and S. So P or true or true, true or false is true, and so on. Maybe I have or. Maybe if I go to the last one, okay, Q and S. I want to get one which is false. So the last one is Q or and S. False or false is false. Now F or F is F, and so on. And you can complete this. Okay. Now, as an exercise, what about if you compute P or Q or S P and Q, or S and R. Oops, this is R. So that you use for propositions. So that you use 16 cases. Okay? And this brings us to the end of this section.